This video is on applying Newton's second law of motion to stacked blocks. Question 1. A pulling force is applied to a block on a rough horizontal surface. Draw a graph which shows the force of friction versus applied force acting on the block. So imagine you have a block here and you're pushing an object to the left. That's the applied force. But the object doesn't move. So if the object doesn't move, force of push equals force of friction in magnitude. The more you push the object and the more it doesn't move, if it continues to not move, force of push continues to be equal to force of friction. The moment the object starts moving, the force of friction actually decreases. So if you push an object more and more and the object continues to not move, that applied force and force of friction increase at the same time. But once the object starts moving, the force of friction actually decreases. So we get something that looks like this. You see, the horizontal axis is the applied force. The vertical axis is the force of friction. The more you push the object and it doesn't move, it's called the static force. And you see that vertical line, it says the instant of motion. Once the object starts moving, the force of friction decreases, even though the applied force increases, and that ends up being the dynamic force. So if you've ever pushed a car at rest, you'll understand in the beginning, when you push it, the car doesn't move. The more you push it, it continues to not move. Once it starts moving, you feel like the force of friction decreased. It's actually easier to move the car. Question 2. A block with mass M2 is sitting on a horizontal frictionless surface. On top of that block is another block of mass M1. The coefficient of static friction between the two blocks is mu. A pulling force F pull is applied to M1, so both blocks accelerate to the right. Part A, use a pencil, label the forces on each object. So M1's on the top, M2's on the bottom. There's a force of friction between M1 and M2. There's no friction between M2 and the surface. So remember, circle the object, label the forces, put an X and Y axis, and then use the equation F equals ma. So those are the forces for M1. Force normal up, force gravity down, force pull to the right, force of friction to the left. And here are the forces for mass 2. Force normal up, force normal 2 up, force normal 1 down, force gravity 2 down, force of friction is to the right. So Newton's third law, which is the law of action and reaction, can be seen in both of these figures. You have a force normal 1 pointing up for mass 1, and you have a force normal 1 pointing down for mass 2. You have a force of friction 1 on 2 to the left of mass 1, and you have a force of friction 2 on 1 going to the right for mass 2. So these are like the same forces acting on different objects in different directions. Part B. When the pulling force is small, the two blocks move together. Determine an equation for the acceleration of the two blocks. So treat the system as one object only. That means there's no friction between the two blocks. So we don't have two blocks, we just have one. There's no M1 plus there's no M1 and M2, it's M1 plus M2. So this is what we get. Acceleration is force of pull divided by M1 plus M2. We just use Newton's second law of motion. Part C, if the pulling force, F pull, is too great, then the two blocks do not move together. Determine an equation for the minimum pulling force in which M1 slides relative to M2. So imagine if you pull mass 1 to the right with a great force. So now mass 1 and mass 2, they don't move together with the same acceleration. So take a look at mass 1, we get this equation here. Sigma F sub y1 equals m1 a sub y1. We get force normal 1 minus force gravity 1 equals 0. And take a look at sigma F sub x1 equals m1 a sub x1. What forces do we have? We have force of pull minus force of friction. So you could see that in this free body diagram on the bottom left. Now take a look at the third equation here. Sigma F sub y2 equals m2 a sub y2. We get this equation here. We get force normal 2 acting up and force gravity 2 and force normal 1 acting down. And finally we get this equation here. Sigma F sub x2 equals m2 a sub x2, which is equal to the force of friction of object 2 from object 1. But this in magnitude is equal to this in magnitude. Force of friction 1, 2 is equal to force of friction 2, 1. So that's equal to this. And we could solve for a sub x2. Now, we're looking for that condition where the acceleration of both objects are not the same, but let's just let both accelerations equal each other. So now we have these two equations in yellow and gray. So we have them in yellow and gray here. Let's add the left side plus the left side and the right side plus the right side. And now we could just solve for force of pull. So that answers our question. Determine an equation for the minimum pulling force in which m1 slides. These four equations are the most important because you're using Newton's second law of motion. Question 3. A block of mass m2 5 kilograms is sitting on a horizontal table. On top of m2 is another block of mass m1 equals 3 kilograms. The coefficient of kinetic friction between m2 and the surface is 0.5. A pulling force of 70 newtons is applied to m2, so both blocks accelerate to the right. What's the difference between problem 3 and problem 2? In problem 2, we have the pulling force on m1. In problem 3, we have the pulling force on m2. So part A, use a pencil, label the forces on each object. So 4 steps. Circle the object, label the forces, put an x and y axis, use the equation F equals ma. So as you can see, Newton's third law of motion can be seen in these two figures. The force of friction between object 1 on object 2 is equal to the minus force of friction on object 2 from object 1. Equal in magnitude, opposite in direction. Also, force of normal 1 on mass 1 points up, force of normal 1 on mass 2 points down. So, same force, same magnitude, opposite direction on different objects. Part B, calculate the minimum coefficient of static friction between the two blocks so M1 does not slip. So we want them to move together. So step 1, determine the acceleration of the system if the two blocks move together without M1 slipping. That means there's only one object. So this is sigma F sub y if there's only one object. So M1 and M2 act as one. So force normal is equal to M1 plus M2 times G. Then sigma F sub x equals MA sub x. which is equal to the force of pull minus force of friction. Remember, this is only one object. We're treating it as one object. So acceleration, solving for a sub x, we get this equation here. We could plug in what we know to get 3.845 meters over second squared. So that is the acceleration, assuming that nothing, m1 is not slipping on m2, and vice versa. Step 2, the condition is static force of friction equals mu static force normal. Why are we saying static? Because they're not slipping, so we have to use static friction, not dynamic. And we get a value of 0.392, and that's what the problem is asking. Question 4. A block with mass m2 equals 6 kilograms is sitting on a horizontal frictionless table. On top of m2 is another block of mass m1 equals 3 kilograms. The coefficient of static friction between the two blocks is 0.650. A pulling force F pull is applied to m1, so both blocks accelerate to the right. This problem is very similar to problem 2. So part A, use a pencil, label the forces on each object. So remember the 4 steps. Step 1, circle the objects. Step 2, label the forces. Step 3, put an x and y axis. And step 4, use the equation F equals ma. So positive x, I didn't write this down or draw it, is to the right. Positive y is straight up. You could see Newton's third law of motion, which is the law of action and reaction, can be seen in these two figures. Force of friction of object 1 on 2 from mass m1 is equal to minus force of friction of object 2 on 1. The minus means the direction. Also, force of normal 1 is pointing up in mass 1, and force of normal 1 is pointing down in mass 2. Part B, determine the magnitude of the maximum force which results in both of the blocks moving together without slipping. So both blocks move together without slipping. So step 1, we have this, sigma f sub y1. Step 2, force of friction equals mu force normal. And we're only looking at object 1 here on the top. Step 3, sigma f sub x2. And then finally step 4, sigma f sub x net. So the net means total. So the mass total is m1 plus m2, and the acceleration is going to be the acceleration of x2, which is this here. So that's our solution. Part C, if the pulling force is too great, then the two blocks do not move together. Determine an equation for the minimum pulling force in which m1 slides relative to m2. So remember, what you should always do is write Newton's second law for the x-axis and y-axis for both m1 and m2. And you could see that's what was done here. So now we have an equation from m1a and m2a. We could add the two equations above because we let a sub x1 equal a sub x2 equal a. And we're going to get the same solution as we did from problem 2. Question 5. A block of mass m1 equals 3 kilograms rests above the flat horizontal surface of a block with mass m2 equals 6 kilograms. Mass m2 rests on a smooth frictionless horizontal surface. We're given the coefficient of static friction and dynamic friction between m1 and m2. So this image looks like problems 2 and 4. So once again, Newton's third law of motion, which is the law of action and reaction, can be seen in these two figures. We have the same force acting in different directions on m1 and on m2. See, force normal 1 acts up on m1, force normal 1 acts down on mass 2. Force of friction between object 1 and 2 is to the left on M1 and it's to the right on M2. So they have the same magnitude, just opposite directions. Part B, determine the direction and magnitude of the acceleration of M2. So we want to know if these two blocks are going to slide with each other or apart from each other. So we need to find that condition, if that's true or not. So if both blocks slide together, then we have this equation. F max horizontally over 9 kilograms is equal to acceleration. Step 2, let's just look at object 1, mass 1. M1 equals A sub 1 equals F max minus F static max. So F max is equal to the max pulling force. F static max is the static friction. Force of friction is mu Fn. That's what we plugged in here. Force normal is M1g. From this line to this line, we just solve for F max. We just move things to the other side. Here we have solved for acceleration, so we're going to substitute for acceleration here. And then we have X max on the left side and the right side, so let's just move X max to the left side. We solve for X max here, which is greater than 7 newtons. That means both blocks move together, because we're going to pull with 7 newtons, but force max is going to be 8.83. So the acceleration is going to be 0.778 meters per second squared. Question 6. A block of mass M2 equals 45 kilograms is placed on a smooth, frictionless horizontal table. Another block of mass M1 equals 15 kilograms is placed on top of mass 2. We're given static friction coefficient and dynamic friction coefficient between mass 1 and mass 2. So remember the 4 rules. Rule 1 is circle the objects. Rule 2 is label all of the forces on the objects. Rule 3 is put an X and Y axis. Rule 4 is to use the equation F equals ma. So remember, if I circled this on the left side for M1, I could only use those forces in one equation. I cannot use the other forces on M2 on the same equation. So once again, Newton's third law of motion, the law of action and reaction, can be seen in these two figures. So why don't we just do what we usually do? We have two objects. We could use the X and Y. We can use Newton's second law for horizontal and vertical motion for both of these masses. So we get 4 equations total. So part B, it says calculate the acceleration of M1 when a pulling force is 400 newtons is applied to M2. So we want to know if 400 newtons is going to be enough to make these two objects slide apart from each other or slide together, move together. So step 1, let's assume both blocks move together. So we get this equation. If they move together, acceleration is F max over 60. Step 2, let's look at the bottom block M2. So sigma F sub 2 equals M2A2, which is equal to force pulling max minus force static max. Here, force of friction is equal to mu Fn. Here, force normal equals M1g. Here we're going to solve for force max. We already know what A2 is. A2 is this, and that's highlighted. So we're going to put it here. It's a substitution. Now we're going to solve for force max. And then we have F max is equal to 353, which is less than 400 newtons. which means that both blocks slide relative to each other. M1 only experiences kinetic friction. So the acceleration is going to be 3.92 meters over second squared. Because kinetic friction is 0.4. Question 7. Mass M1 rests on top of mass M2. A pulling force of mass M2 acts towards the right. The coefficient of static friction between M1 and M2 is mu12. The coefficient of dynamic friction between M2 and the horizontal surface is mu2, comma s. S means surface. Mass 2 and the surface. So part A, label the forces on each object. Remember the 4 steps. Step 1, circle the object. Step 2, label the forces. Step 3, put an x and y axis. Step 4, use the equation F equals ma. So, part B, both masses are moving to the right together with a constant velocity. Determine the force of friction from the surface on M2. So, let's treat the system as one object only. That means that there's no friction between the two blocks, since we don't care about internal forces. Because it says they're moving to the right with a constant velocity together. The key word here is together. How do you spell together? To get her. Isn't that cute? So that's why M is equal to M1 plus M2. So force of friction is equal to force of pull. Part C. Now both masses are moving to the right together with a constant acceleration. Determine an equation for the maximum force of pull in which M1 does not slip. So Newton's second law in the vertical direction for mass 1 is here. Newton's second law in the horizontal direction for mass M1 is here. Newton's second law in the vertical direction for mass M2 is here. And Newton's second law in the horizontal direction for mass M1 is here. So we're looking at this image here. So the conditions for no slipping is this. So we have these two equations here. Force of friction is equal to mu force normal, and here force of friction is equal to mu force normal. So now we have this equation, and we have this equation. So we're going to use this green equation and solve for force of pull. And this is equal to force of static friction between 1 and 2. Why? Because we have it here. And you could see this third equation here. We have a force of static 1, 2 here. We have a force of static 1, 2 here. So we could factor those out, which is here. Then we could substitute in again. And this is the equation we get.